Without further ado, I'll turn it over to those folks. We are recording this session, and please feel free to use the chat, and we'll be doing our best to moderate responses in real time. So with that, I'll turn it over to the workshop leaders.
All righty, thanks very much for the introduction. That's great. I hope you guys can hear me. I'm going to start sharing my screen now.
We can hear you great, thank you.
Awesome. So, welcome to Dask Summit. Why this is so big? There we go. Okay. So, first of all, welcome everyone. This is Dask Distributed Summit 2021. And as we already know, we are in the session that we'll be talking about Dask SQL Query Engines. I'm Tom. I work as a data scientist for Blazing SQL, and I'm joined here with Nils, Han, Mike, and Miles, who will be talking about different SQL engines for the Dask ecosystem. I'm going to let them introduce themselves, but we're going to start with a brief introduction to Blazing SQL, to Dask SQL, and then Fugue. We're going to have a demo for you guys to see how easy it is to get started with either of the technologies. And we're also going to have an introduction and then showcase how Dask can easily integrate with the Snowflake SQL engine. So without that, let me quickly give you a rundown of what Blazing SQL is. Blazing SQL is a GPU accelerated SQL engine. What it means is that instead of running everything on a CPU, our engine takes every single computation that you required it to do, expressed in SQL, and runs it on a GPU. I don't know what this is. There you go. So we are part of the RAPIDS ecosystem. Blazing SQL is pretty much using the whole, pretty much the same libraries that are written for NVIDIA RAPIDS ecosystem. And we go hand in hand with RAPIDS and Dask. So whenever you run a query using Blazing SQL, you either get a return as a cuDF data frame or Dask cuDF data frame, depending on whether you run in a distributed mode or on a single GPU. Why this is going like this? So as I said, we are part of the RAPIDS ecosystem. So you can think about this whole data science life cycle to be when you prepare the data and then featureize the data. So that's where you would use either Blazing SQL or cuDF. So I always like to say that whatever is easier for you to do in either SQL or Pandas-like API, then you can either have a choice whether you're going to use Blazing SQL or cuDF. And once your data is prepared, you can go over to QML, cuGraph, which is the, QML is a machine learning library for RAPIDS, and cuGraph is the graph analytics library for the RAPIDS ecosystem. There's a bunch more libraries that are already available in the, the whole ecosystem. But the whole underpinning of this is the Apache Arrow. So no matter whether you run on a CPU or a GPU, the memory representation of the internal data structure is all run using Apache Arrow representation of objects, and that enables us to quickly move from one format to another format without really necessarily copying the data over and over and over again and converting that, losing the time to actually do that. So if you do something on in Python on a GPU, you can quickly move to a C++ representation of the same memory space and then run a kernel, CUDA kernel on top of that. In terms of the RAPIDS ecosystem, I already touched a little bit upon that, but we are on the featureize side of things. So we kind of go hand in hand with the cuDF, which is and QIO. QIO is the the readers and writers part of the ecosystem. QML and cuGraph I already mentioned. If you want to do deep learning, you have options to use PyTorch, Chainer, MXNet, and whatnot. I believe TensorFlow is already also supported. all of these, conversions from, let's assume that you want to do all your data preparation using GPUs, either with Blazing SQL or cuDF. You can quickly then move to either PyTorch or Chainer or MXNet via DLPack. So you convert the internal representation from cuDF data frame or Blazing SQL, output, i.e. Dask cuDF or cuDF to DLPack, and then PyTorch and Chainer can actually read that back directly from the GPU. So you never kind of leave GPU that way. And also, if you want to visualize the data, we have cuCross filter or cuData shaders that allow you to visualize millions of data points at a time and pretty much manipulate them in real time. In terms of Blazing SQL, Blazing SQL is a SQL engine, right? So we are not necessarily a database. You can point and create table from pretty much all the data formats that RAPIDS ecosystem supports. So it can be a CSV, Parquet, tab delimited, files, org files, and JSON files and whatnot. But you're also able to create a table, just like in this particular example, from a cuDF data frame. So first here we read the data frame from a from a CSV file into into a cuDF data frame, and then we can quickly create a table on top of that to start querying this. In this particular example, we count how many records we have in this particular table. Underneath the hood, what Blazing SQL is using is that, of course, on the top, our API is written in Python. So whatever you do, you kind of interact most of the time you would interact with this in Python. We use Cython to manage the communication between Python and the underlying C++ layer. So the whole engine is written in C and C++, and we use CUDA libraries to do the actual work. But just like Nils is going to talk to you about, Apache Calcite, we use JPipe to communicate with Apache Calcite to get the relational algebra from Apache Calcite. Apache Calcite is a SQL query parser that takes the SQL queries written as strings and then returns a logical plan to execute by any engine, right? So just like, we as Blazing SQL use Apache Calcite to create the relational algebra for our engine, Nils is using that for, for doing Dask SQL. Underneath the hood, we use CUDA libraries. So most of this is running, pretty much on the GPU. And we use Dask. So that's why we're here. We use Dask to enable the communication between the nodes, but the communication not necessarily in the actual Dask way. So we use Dask to send messages that, okay, here's your, relational algebra, and then, you work node do your work. Most of the communications from that point on is actually handled by the engine itself. So that's why it allows us to use, TCP or UCX. UCX currently is in experimental mode to communicate and exchange the messages engine to engine. So every single worker node is actually running its own Blazing SQL context, local Blazing SQL context that is running on its own, subset of the data, its own partitions of the data, and then all the communications that are actually work related happen in a different layer, while Dask is waiting for us to finish. Once we finish, we communicate with Dask and return the results to the the scheduler. So Blazing can be distributed, as I said. The Dask process is a Dask client calls C++ APIs, and then any file system, any table that we create is actually getting registered with the engine itself. So most of this work happens in the C++ layer, and just like I said, communication as well. All the SQL calls, whenever you want to run a query using SQL, it runs to two main calls. So we first generate the graph, where we call the Apache call site to get the logical plan of execution, and then we create our own execution plan, the physical plan. And then the second call that gets shifted to to all the worker nodes is to execute that plan or subset of that plan that is relevant to the worker. Why? There we go. So in terms of you want to start using Blazing SQL, it's extremely easy. Pretty much from after you've installed the package through pip, or you can use Conda, you can use our Docker image. Blazing SQL is also part of the Conda channels and Blazing and Docker image from Rapids. So if you download Rapids, you get Blazing SQL for free. Simply you import the Blazing context from Blazing SQL, start the Blazing context, register S3 bucket, for instance. You don't have to, but in this particular example we do. Create a table, so you can, as I said, you can create tables on top of pretty much any file format, but that file format doesn't have to be local to your machine. It can be remote. As in this particular case, we have a plugin to read data directly from S3. So if you run your compute on S3 on AWS, you can quickly just point it to register the S3 bucket that you have your data in, and then run the queries on top of that, and then run your SQL query. So this is pretty much how would you start on a machine with a single GPU. If you want to start a Blazing context in a distributed way, all you have to do is to create a client and pass that client to the Blazing context. From then on, everything happens pretty much the same. All the queries stay the same. You create tables the same way, and then you use the Blazing SQL query the same way. All you have to do is just to pass the Dask client, and that's it. So I know I'm rushing a little bit. We're going to have the Q&A during the demo. So and if you have any questions, you can also put them in the chat. But this is pretty much it from me. And I'm going to pass it on to Nils right now to introduce Dask SQL to you guys.
Thank you very much. I think you need to stop sharing, Tom.
That's exactly what I was looking for. Thanks.
Perfect. Thank you very much. All right. That was the wrong one. Here we go. Okay. So I'm going to present to you Dask SQL. I hope you can see my slides now. Perfect. Thanks, Tom. As Tom said, Dask SQL is quite similar to what Blazing SQL is, except that it works natively with the Dask data frames. This means it's meant to be run on a CPU cluster. So Dask SQL is kind of a distributed SQL query engine written in and for Python to help you combine the power of Python and SQL. As you've seen in the example that Tom has shown, you can really natively go from your Python code to SQL code and back however you want, and just use whatever is easier for you. It's the same easy installation for Blazing SQL and Dask SQL. It's really just a pip install or a conda install. We have Docker images available for both of them. And now the difference to what has Thomas shown, Dask SQL runs on your CPU cluster. And CPU cluster could mean just your local computer, just your laptop for development, but could also mean scaled up as large as you want in the cloud or on-prem, or basically on every cluster that you can think of, because Dask can really run on a lot of machines. And as in the end, everything is just a Dask API call in Dask SQL, you can use the large number of integrations that we already have in the cool Dask ecosystem. Like S3, HDFS, you can talk to Hive, you can talk to an intake catalog, you can talk with Apache U, with Superset, you can use Dask machine learning, you can deploy in a Kubernetes cluster with Apache.
You order this one or no?
Or whatever you want. So I will really quickly walk you through.
I would say that maybe
there's a bit of noise in the background. I will walk you very quickly through how Dask SQL works. The idea behind it is you have this SQL engine, and you can really interchange in this slide Dask SQL and Blazing SQL because they're both using a very similar idea. You start with the SQL engine, which is a client-only application. and it you enter the SQL code. Could be, for example, just as a string of the SQL string. Dask SQL also brings a server application where you can use, for example, you can connect with your BI tool. And then this string gets parsed by Apache CalSite. I will come to that. It would then get converted into either Dask distributed API calls, this in the sense for Dask SQL, or as Tom has shown, calls for your GPU written in C++, and then gets distributed over over the cluster, and can then, for example, access data on S3, HDFS, or whatever. Really quickly into some of the details. So we'll try to walk through how this query, select maximum of price from some data, group by month, would go through the full process in Dask SQL. And as I said, it's pretty similar in Blazing SQL. So we start with this SQL as a string, for example, could be in your Jupyter notebook, could be in your Python file, or could be in your BI tool. And the first thing that happens is it gets converged in a so-called relational algebra. This is done by Apache CalSite. There's a lot of magic happening. It's not just only the parsing. There's also a lot of optimizations going on, like things like filter pushdown, if you know what that means, for example. But in the end, you end up with this relational algebra. You can kind of see maybe the original SQL query here. We have a table scan, which means just grab information or grab the data from this specific table. You can see a project, which means and select only those two columns. Then we have an aggregation, which was our group by, which was a maximum of the first column. And then we just project out the result. And for that, of course, we need to have some sort of storage, some metadata storage, where you can see which tables are currently registered. And that was exactly the context that Tom has shown, and that also is present in Dask SQL, actually. Yeah, just we will share the slides later. I won't go through all the details, just for you some examples. Every SQL can be transformed in these kind of relational algebras. And the nice thing is, once you have these relational algebras and once they are optimized, you can go ahead and transform them one by one into calls to, for example, the Dask API. And yeah, I'm also rushing through those slides. We will share them later. So there's a lot more information on the slides that I will not talk about now, because I want to showcase this one here. So now we have a one-on-one conversion between these relational algebras, which we get from Apache CalSite. And then for Dask SQL, just Dask data frame API calls. You can see we have a table scan, which is basically just getting the table from the already registered tables in our context. Then you have the project, which is just, well, getting those two columns. We have the aggregate, which is a group by and maximum on the price. And then, yeah, we project out the corresponding results. So this is the magic basically happening in Dask SQL. For Blazing SQL, it's a bit more complicated because you also need to converge to those C++ kernels. But in principle, this is what's going on. And if you want to have this distributed, well, this is where Dask comes in. Dask will then take care of distributing this calculation to your cluster. Of course, if you want persisting it, caching it, and comes with all the nice things as resiliency, retries, and all this stuff. So again, they can get back the result if you want. So that was a very quick walk through the internals of both Dask SQL and Blazing SQL. I do have maybe one slide, sorry. One slide to show you really quickly what are the most important differences between Dask SQL, Blazing SQL, and Fugue that Han will present in a minute. So again, the most important difference between Blazing SQL and Dask SQL is that Blazing SQL runs on GPUs and Dask SQL runs on CPUs. So Dask SQL uses internally calls to the Dask API, to normal Dask data frame API, and Blazing SQL use their C++ code. That means Blazing SQL is really fast on everything which you can do on GPUs. And Dask SQL is nice because it runs on a lot of clusters without CPUs and in many, many different configurations. Both have a very simple installation and setup, and Blazing SQL also has a nice logo, which Dask SQL is still missing. And Fugue, and Han will present that, is kind of the bracket around that, where you can mix and match even different of those SQL query engines. And with that, I would already end the session on Dask SQL. So I'm gonna go back and stop sharing. And hand over to Han.
Hello. Hey, let me share my screen. Share screen. Everyone can see, right?
Yes.
Awesome. Hey, thank you, Nils and Tom, for the great presentation. And hello, everyone. My name is Wang. Blazing SQL and Dask SQL are wonderful. And now I'm going to talk about Fugue and Fugue SQL. They will make your experience with Blazing and Dask SQL even nicer. So all packages I will talk about today are already open sourced. For Fugue Core and Fugue SQL, please install the Fugue package. And for GPU and Blazing support, please install Fugue Blazing. So what is the motivation of creating the Fugue project? In the past, we created our own computing logic to run locally using simple Python and SQL code. But in order to scale out, we have to use certain distributed computing engine. In order to use a certain distributed engine, we normally have to adopt their API and interfaces, making our core logic convoluted and hard to maintain. So instead of learning and adapting to a certain frameworks from the user side, what about creating an abstraction layer that can adapt to both users' codes and different computing engines? That is the motivation of Fugue. It is to hide the complexity and inconsistency of different computing frameworks and provide a unified approach to do distributed computing and machine learning. And in the meantime, Fugue keeps being non-invasive and minimal to users' logic. We want to bring scientists and data engineers back to their core tasks. With this design, since the core logic is written in simple ways, they are already very easy to do unit test. Plus, Fugue can let you use local execution engine and mock data frames to run your data pipelines end-to-end without Spark, Dask, or Blazing SQL. Your entire pipeline becomes testable. And more importantly, you can use this approach to quickly iterate on your local bugs. And you can do enough testing before pushing to the expensive computing cluster. Last but not the least, both your core logic and the Fugue level code is platform agnostic. So you can easily switch between Spark, Dask, Blazing SQL without any code change. Here is an overview of the Fugue projects. There are different computing frameworks: Spark, Dask, Pandas, and on GPU we have RAPIDS and Blazing SQL. Fugue is an abstraction layer unifying the computation. And on top of Fugue, we already have Fugue SQL, validation, and a tune. And today's topic is Fugue SQL. Now let's talk about Fugue SQL. If you have ever used the SQL in your Python workflow, you will see this common pattern. You write a block of Python, then you invoke SQL to do something, and then get the data frame back, and then repeat. the code will be very convoluted by switching between Python and SQL. This seems inevitable because Python is the dominant language here, and SQL is not designed to support multiple statements. SQL solves this problem by adding extra syntax to the standard SQL. So you can easily describe your end-to-end workflow using SQL as the dominant language. And in addition, you can also write simple Python functions as extensions that can be directly invoked by SQL. We will see them in the demo. And commonly, you will see your code becomes significantly shorter with much better readability. I also want to mention that SQL can use Dask SQL, Blazing SQL, and Spark SQL as the backend. And it can also run without any of them. And that is why SQL is very unit testable. Now let's take a look at an example. We want to compute the median of column D of a pandas data frame, and then get the difference of each D and the median. It's quite simple to express this in pandas, but it's not easy in SQL. So we write a Python function using pandas. In this compute example, we have two data frames as input. We want to join them and get the product of B and C as column D. We use SQL here. And then we want to do two things. One is to compute the diff from median for each group. Another is to take the smallest n rows from each group sorted by B and C. On the left side, it is how we do that using Dask SQL. And we have to write another first n to do the second thing. Now let's see how to express the same logic in SQL. We only need a single block of SQL code. We define and assign the joined data frame in a way like Python. And to compute median diff, we can also directly invoke the median diff function. And we don't have to care about meta, which is a specific thing to Dask. And to get the first n rows of a group, we don't even need to implement anything. We have the take statement to handle that. Actually, take can be significantly faster than the Python approach with certain execution engines. And please pay attention to engine. Compute 2 is no longer only for Dask. It can run on cuDF and Blazing. It can run on Spark, and it can run without any of them. That is how you do unit test. You also have a lot of flexibility on the input. df1 and df2 can be a mix of pandas data frame, Dask data frame, and cuDF. And the engine can be a combination of Dask engine plus Blazing SQL engine. So your SQL will execute as Blazing SQL, and the rest, like the transform, will use Dask to do distributed computation. You will see more detailed examples in the following demo. Again, everything I talk about is open source. You can try them by installing them. The example of SQL with Dask and Dask SQL is also available on Kaggle. I will share the link. Thank you.
All right, thanks, Han. That's well, now you have it. You have 3 SQL engines that are available to you in the Dask ecosystem. So you have a choice between running things on GPU, CPU, or abstracted away, and pretty much focus on mostly on the SQL side, and have the ability to unit test and do whatever you want pretty much using Fugue. So I don't know if we want to have 2 to 3 minute break before we jump into the demo, or we kind of carry on with the demo straight away. Show of hands. Let's see them. I don't know if this is possible. I don't see it. All right. There's reactions here. I didn't know that. Sorry, I'm bubbling. Hi, Matt, by the way. I just saw you over there.
Yeah, so for context, there are reactions in the bottom of Zoom if you want to give a thumbs up. So you see Abru and Scott just gave thumbs up.
Okay.
Which I think means do a demo now or do a demo later. I actually don't know which. There's also a small enough group, people can just say things. I think it's, or talk in the chat.
Okay, I'm gonna make an executive decision. Let's take a 2-minute break and we'll be back at 7:34 for me, which is whatever 34 minutes after the hour for you.
Sounds good, thanks.
2 minutes.
All right, it's 7:34 on my clock, so we might as well get this session rolling further. What you see currently on the screen, and I already pasted the link to to the GitHub repo for this session to the chat window. Han and I and Nils, we prepared some demo notebooks for you, so you can go and clone this code and follow us along as we go through through the notebooks, or you can look at them later on and see if something sparks your interest. So everything's gonna be ready here. I believe I'm gonna definitely make some changes, so the content here might change a little bit. There's also already some data that we're going to be going through today. This data set is part of the Bureau of Transportation, I believe, statistics, and it contains information about all the flights that departed, in this particular case, I believe, in January 2018. In the continental US, it includes, flight on time and whatnot. But first things first, let's get this started. So, of course, we do imports first. We import QDF, we import Blazing SQL. S3FS, this is optional in this particular context, but I'm including that if we were to read some data from S3, we have the usual things that you call import for working with notebooks. We also have In this particular case, I'm running on a single GPU. So this is my local box. So I will be creating a local CUDA cluster, which is a GPU equivalent of a local cluster if you're coming from a Dask CPU ecosystem. So it allows you to test your distributed code locally on your machine. And we're getting also the client. So I'm going to run this. And then we are starting the cluster. And as I said before, we pass the client to as a Dask client parameter to Blazing Context. So therefore, Dask can use this. Blazing SQL can use Dask to distribute the workloads. In this particular case, this is a quasi distributed because we are running on a single GPU, but it still allows you to to do that. Now I'm going to start this, and let me tell you a little bit, very brief, high level, about the arguments that you can actually use to start Blazing Context. There was a question in the chat asking about what happens if I have a GPU with 16 gigs of RAM or 24 gigs of RAM, and my data set is much larger than that. Do you allow to spill over to hosts or whatnot? And the answer is yes. By specifying the allocated, which actually defaults to, I believe, managed, it allows you to automatically, if you are running out of memory on a GPU, spill directly to either host memory, or in extreme case, if the host memory cannot hold the data, spill to disk. We use this unified virtual memory, which is part of Rapids Memory Manager, that allows you to actually do this. I personally have been successful running queries on 1 terabyte data set on a single T4 GPU with 16 gigs of RAM without any problems. And yes, definitely you can do that. The Dask client we have used here, so this allows you to, if you have a cluster of, GPU machines, you can create a client just like we did over here and pass that client to Blazing Context and get on with it. I believe we also support that if you pass, by default, if you have a local CUDA cluster running and you do not pass this parameter to the Blazing Context, we automatically will check whether there's a local CUDA cluster running on your machine. And if yes, we'll still tie Blazing Context to that running cluster. Enable logging is probably less. This is more for if you try to debug something. Initial pool size and pool. So this is the another kind of performance performance switch that allows you to specify the initial allocation of memory of your GPU memory. So if you specify the pool set to true, by default it's false. If you set it to true, Blazing SQL automatically, if you don't pass the initial pool size, it will automatically pre-allocate half of your GPU memory. So later on, Blazing SQL or actually the Rapids Memory Manager doesn't need to do this CUDA alloc and CUDA malloc and whatnot, underneath the hood, wasting time doing that. This way, it's it automatically pre-allocates half of your GPU memory to be specifically and only used by Blazing Context. If Blazing Context needs more memory than that half, it will then allocate more, but at least you have the head start by doing this. And then the network interface, if you run in a in the distributed way, right? So you have your local machine connecting to a remote cluster. We actually need you to specify the network interface you will be using to communicate with your Dask scheduler. It defaults to ETH 0, but you can specify anything that you want. So for me, for instance, if I run on a in a Docker, it would be, I believe, LO or something like that. Anyway, so this is just the a bunch of parameters you can fine-tune the Blazing Context. There's a whole lot in config options that you can tweak and change. All of this is available on our, in our documentation, described in our documentation. So the documentation is docs.blazingsql.com. Let me now try and see if I can connect to the dashboard so we can see everything. 97, I guess not. Search for, there we go. Okay, progress. And I want to see where's my task screen? No, I don't see anything. All right, this is not working for me today. So I will have to just run with what we have. As I said, I am running on a single GPU. So I have a single GPU. You can see that once the Blazing context is starting, it actually pre-allocates a small chunk. In this particular case, because the pool is, defaulting to false, it did not pre-allocate half of my GPU memory. But if I were to set it to true, it will pre-allocate pretty much, I believe, 12 gigabytes of memory, because this is a 24 gigabyte card. So you can do, as I showed you earlier, you can read the data, into a QDF. In this particular case, you can, this data set is also available on our BSQL bucket on S3. This is a publicly available, AWS S3 bucket. So you can just literally go to this location and then just read the data directly from over there. Just don't forget that you need to specify the ANN switch to be true. And then you can do, the usual things you do with S3. But in this particular case, we are using a local file, which sits in the data folder. So if I run this, we have one Parquet file over there, which is, it's actually January 2020 data set. So reading the data into QDF, this is a Parquet file. So we will use a QDF read Parquet, read Parquet from this. The storage options here is unnecessary unless you specify the S3, but it tells you that you can still, use and read the data from your local file without really, changing much between S3 and your local file. So it took us less than a second to read that data. We have the top 5 rows that from this particular data set. So as I said, this is a data set that contains pretty much all the flights that departed in January of 2020, and you can see there's a marketing carrier WN and the flight number and the tail number of the aircraft that departed, and then how long it was planned to fly. So CRS, it's the computer reservation system. This is part of the airline, airline industry reservation systems. So it was planned to fly, a elapsed time of 95 minutes, but it actually, actual elapsed time was 122. So airtime was 74 minutes out of that. What was the distance, and what was the carrier-induced delay, and what are the induced delay, and then NAS-induced delay, and whatnot. So it tells you, pretty much everything that, the metadata about the flight, that what happened. Less, I don't think we have the amount of passengers there. Just like with the, with pandas, in order to get the number of flights, you can just run the, give me the length of a flight from this particular case. So we have 660,000 flights in this particular example. With Blazing SQL, it's equally easy to do things. So we can literally point a create table, command method to the list of files that we've created here, right? And Blazing SQL will happily create an air transport table on top of that, and then give us 5 rows back. Well, in this case, of course, because we are running on a Dask local cluster, it will return a Dask QDF, which is effectively not doing anything as of yet. It literally just returns to you, here's what I'm going to give you when you ask me for it, right? So if we ask for it by saying the .compute, it will actually, why this is happening? it will actually, do the proper work and then, run the query and then retrieve the 5 records, from the data set, which are exactly the same as we had, earlier with QDF. Now, I want to point you to these 2 things and kind of tie it back to what I said earlier, that certain things are easier when you do things in a pandas, PyData, way of things, and then some things are easier when you actually do them using SQL. Running the, counting how many flights I have in this particular data set with QDF, with the pandas, is simply by, checking what is the length of the data frame itself. With SQL is a little bit more typing and then, taking out and then retrieving you get the same result back, but it's a little bit more convoluted. Now, I'm going to skip over these. So, you can retrieve the list of columns and data types from both of the, objects. But what I'm trying to point you to is we also have 2 additional data sets. So airports and airlines. Airports contain all the metadata about the airports. So we can join that with the flights data set. And then airlines, they have information metadata about the airlines themselves. So if you look at the airports, it will tell you the name of the airport and city and country and whatnot. And the join column is the IATA or ICAO, which are the international standardized, codes for airports. And the same thing goes for airlines. So every airline has an IATA and ICAO, call signs that allow you to kind of recognize them in their systems. So if we were to create tables on top of that and join these 3 tables together, right? So what we do here is we select stuff from the air transport table that we created that contains all the flights. So we will retrieve the flight date and operating carrier. But we also want to bring on, okay, what was actually the name of the airline that actually, flew that flight, and where it originated, what was the name and the city of the origin airport, and then what was the destination and what was the name and the city of the destination airport. So we actually do 3 left outer joins, once to airlines and twice to airports because we have origin and destination. And in SQL, it's super easy, right? You just literally run this, less than a second, you have the result. You have, flight date, and you have the operating carrier, the carrier name. So AA stands for American Airlines. It started from Portland, so PWM, and flew to Charlotte, right? So Charlotte Douglas International Airport. That's super easy. With Blazing SQL, we can also, if you have a data set that is, a CSV, you don't need to read it, using QDF directly into, into QDF data frame. You can point it to that particular, CSV file, and pretty much all of the, switches that are available to you in the read_CSV, API from Rapids, you can pretty much pass them on directly to create table. And then Blazing SQL will, use those to properly parse the CSV file. And then the same thing will happen here. But if you compare that, and if you were to do that natively with the Pandas, API, it will look like this. It's going to do the same thing as we did before with SQL, right? So you still get the flight date and the operating carrier and then origin destination, just not sorted in a way. But it's a little bit, it's in my opinion, much less readable than actually looking at this and like, I know what's happening here. Whereas for me, for this particular case, it's still readable, but it requires more, delving in and then just trying to decipher what's happening. So tying it back, for me, having either Blazing SQL or Dask SQL View, being able to, do things both ways. You have the ability to do things both ways. You have the option to do SQL. You can, if you wish, you can do everything SQL, and and it's still going to work. But certain things are much easier with certain, one API, and certain things are much easier doing, SQL, for instance. Therefore, you have the, ability to kind of maintain your code in both ways, whichever is easier for you to solve a problem at hand. So that's the beauty that I see both in any of the SQL engines that we are trying to show you, today. So this is another perfect example, counting how many unique airports we have in the data set. With the Pandas API, this is super easy because this is just len of unique. Whereas with SQL, it's like select count distinct origin as count from this, and then compute that, take the count column out of the result, and then take the first element of that. So you get the same results, 365 distinct airports in this particular data set, but it's a little bit less readable. However, if I were to express this in a purely Pandas API, it would be much more complex to actually to deal with. I'm running on time, so I'm going to hand it over to Nils right now. To walk you through, the example for Dask SQL. Nils, are you there?
Yes, I am.
Okay, so how do I stop presenting? Hold on.
So maybe before I
yeah,
start, are there any questions to Tom? And I still hear some background noise.
So I see one question that was that popped into chat, is it compatible with NVLink, and does it work on top of that? So the answer is yes and no. We have UCX currently in the works. It's still in the beta. So technically it should work, but we have not tested it yet well enough in order for me to say yes, go for it. So there still might be some issues here and there where things might not work as intended. If there are any other questions, I'm happy to switch to chat right now, and I'm gonna give Nils the floor. Thank you.
Perfect. Thank you very much, Tom. So as we said multiple times, Lazy SQL and Dask SQL, the difference is not super large. That's why basically all the SQL queries that you've seen in Tom notebooks, you can directly copy and show them all, use them also with Dask SQL. That's why I'm going to skip introducing you to the data set and all these things, because you've seen these parts already. So I have very similar imports here. Instead of using a local QDF cluster, I'm just using a typical local Dask cluster. And on the right-hand side, you can already see the dashboard that you probably all know, with some task streams and the number of bytes which are stored on the cluster currently. So this is really just a normal Dask cluster. You can put in here whatever you want. Could be a cluster running on Yarn, could be a cold cluster, could be a cluster on any of the cloud providers. Dask SQL will run with all of them. One thing to note here, they're similar to what Tom has shown, multiple possibilities to actually run the SQLs. Either you just pass it to the context.sql, so C is my context. In Tom's example, it was BC. So we'll get back here a Dask data frame, not a Dask QDF data frame, but a Dask data frame, the usual one that you probably know. You can call .compute, or you can tell the SQL function to return directly a Pandas data frame, so call the compute basically. Or for Dask SQL, there's also notebook integration that you also will see in Fugue, because Fugue has first introduced this notebook integration. So you can write SQL directly in your notebook, and that's what I will use in the following. So also I have just downloaded the data before the session, so I will use local data. So you see, I will skip those mostly, but instead of using QDF read packet, I'm just using the Dask data frame read packet, and the rest is really, really similar to what Thomas just showed. So let's skip that part. So I will also produce this joint data set. As I said, really the same code, just using the notebook integration. One thing that we can do in Dask SQL instead of just like showing it here and having it in our notebook, we can register it as a new data source for Dask SQL. So we have here our kind of usual create table command that will register the output of this query as a new table. And then in our new queries, we can just reference our info and it will go back to this data frame and actually get the data from there. So you see in the background, it's really just Dask data frames, the usual ones that you know. And you see also here on the right, whenever I call something, you see something's going on our local Dask cluster. And now I can just query it and, for example, get the first 5 elements. Okay, so let's go into some examples here. I can, for example, do a count. So you can really do whatever SQL commands that you're used to. Both Blazing SQL and Dask SQL implement a large fraction of the SQL standard. Not everything is already implemented. So you might find some functions here or there that are not already implemented, but there's a large fraction is already there. For example, you can extract the day of the week and also group by that. So for example, we can find out what is the average delay that we have on our days of week. So from Sunday to Saturday, what is the average delay that we had in our flights? You can see when you go through the week to Saturday and the weekend, that then we have the largest delays. We can, of course, do the same thing for our day of year. This is only data for the January, so we'll only have the first days of the year. But what I want to show here is that in the end, everything boils down in Dask SQL to normal Dask distributed calls. So I will not compute data frame directly here. I will just like store our non-computed data frame in df. So you see there's no .compute here. df is, as Thomas called it, really just, I will calculate something if you tell me to do so. And for example, I could now use the visualize function on the data frame. And you see, maybe if you have worked with Dask before, it will boil down to a typical Dask computation graph. You see here, we have 38 tasks that made up this computation. And that's because these SQL calls will get translated into normal Dask API calls. In the end, you could also do the same thing just by writing normal Dask code. To go back, what I've shown you in the talk, you can also visualize the relational algebra that comes from Apache Calcite with the explain function. Or finally, you can just call .compute to get the result. And then the result will be a pandas data frame that you can, for example, just use for plotting. And you see here the average delay on the days in the year. So I don't want to bore you now with many different SQL commands. Just really quickly, what are the different options that you have, what's already implemented? Dask SQL, things like the typical functions in SQL, like cast, or what we see here, we have subqueries. So we have a select statement to get the origin, and we want to calculate the ratio of how many flights are delayed to all flights. So we need to first of all extract all flights, which we just do with a count star. And then we need to extract the flights which are delayed, and we define a delayed flight by just having a department delay greater than 0, and we count only those. And then we do this in a subquery here, group by the origin. And finally, we can just divide the delayed flights with all flights. And you see here on the right-hand side, there's a bit going on. It took a bit longer because this is just running on my local laptop. But in the end, you see that, for example, the Pago International Airport has a delayed ratio of 77% by just 9 flights in total. So that's a lot of delayed flights. You can use things like with, which you might also know from your normal SQL, but you can also use the Windows function. So here we, for example, have, we want to extract what is the flight with the largest delay per airline. And doing that would be a bit of inconvenient with pandas or with Dask. But with SQL, if you know Windows function, it's actually quite clear. So first of all, for each of the airlines, you group flights by their delay. You give them a row number by just counting. And then you just use those which have a delay order of 1. So just the first one. So that would be one possibility. That is now a bit more complicated Dask operation with a bit more complicated Dask graph. But in the end, you end up with 1 line per airline. So here we have, for example, the different airlines. And then we would end up with the flight which had the highest delay. Okay, let me just quickly skip to the last example. User-defined function. So that's also something which is implemented in Dask SQL. And the nice thing is, because in the end, as I said, everything boils down to normal Python Dask API calls. There's no overhead in using your own user-defined functions. So for example, here we have a function that converts our day of week as a number to a human readable text, just for us to see because it's nicer. So that's a function which is very easy to write in Python. So we just have here our list of weekdays, and we have a small lambda function that we can apply to our series of days of weeks, which are numbers, and we convert them here with this weekdays list to strings. We can register this function at the Dask SQL context, but just tell them, okay, here's the Python function. We give it a name so that we can reference it in our SQL later. And SQL is a typed query language, so that means we need to fill in the types. So we go from our integer, which is our day of week, to an object, which is a string. So now we can use, after having it registered, we can use it. So for example, here we extract the day of week from our date, which we have seen is a number between 0 and 6. And then we call our HR day of week function that we have registered here. And we can use that, for example, in SQL, it's like a normal function. And we would end up with a more human readable data frame that we can then, for example, also use for plotting and to have a bit nicer bar. Of course, you can do whatever you want in these user-defined functions. Could be just simple functions as we have seen, could also be more complex things. If, for example, it's much easier to put your transformation function in Python than just do it like this. You could even go ahead and do very complex things like machine learning. Dask SQL comes also with very alpha support for machine learning in Dask SQL. So there's syntax for that to kick off your training and prediction right from your SQL statement. So you do not even need to leave your SQL, and you could even use that, for example, from your BI tool. Okay, so have a look into the notebook if you want later. And if there are questions now, I'm happy to answer them, or also in the chat, and also later, of course, in the Slack channel. But with that, I would end my presentation on Dask SQL and hand over to Han to show us how both of those things can be used in Fugue.
Thank you, Nils. Let me share my screen. This one.
Nils, I think there was a question, and the question was, what
Yeah.
does the complexity of the underlying graph of an inner join look like? I don't know if you want to take that one on.
Yeah, good question. So depends on if you have an equi-join or not. If we have really an equi-join, like I want to join on left column equals to right column, that is easy because we can really just fall back to a merge in a Dask data frame, and just need to do a bit of like bookkeeping of the columns before that, so that we can join on the columns. If we have a more complex operation, that's harder to do. So in I think both Blazing and Dask SQL, we try to like sort out those more complex filters between everything which is an equi-join, so where we can see left column equals to right column and the rest. And then we kind of do everything which is easy on the merge, and then we just do the filter later. And if it's really the hardest case where you have no possibility to join on left column equals to right column, you need to do basically a cross product of all the rows and then filter later. So this is really the most expensive one to do. It is possible in Dask SQL, but will be definitely quite slow because there's a lot of shuffling involved. But as long as you have an equi-join, or at least some parts of your join condition are left column equals to right columns, we can do some optimizations. So I hope that answers the question. If not, I'm also happy to discuss maybe privately. I can show you like what happens in the different steps in this join.
Okay. Thank you, Nils. Let me share my screen. Oh, share your computer, please. So for my side, I will just play the pre-recorded video so that the time will be well controlled. Hello, everyone. Welcome to the Fugue SQL demo. First of all, let's set up the environment. This setup function will register the metrics, enable the highlights, and also created a couple of shortcuts for using Fugue. And this part is to declare that Dask SQL will be the SQL engine for Dask execution engine for Fugue. Okay. After we do that, let's start. First of all, we want to load the metadata into memory as data frames. And this is how we do that in Fugue SQL. Because both of them are CSV files, we can say we want to load the CSV, and neither of them has the header, so we have to be explicit on the schema. And then we just yield the data frames. After we yield, we are able to consume these data frames in the next cell. And actually, this is just a plain pandas data frame. Okay, now let's think about downloading the flights data directly from the internet. First of all, let's download just one partition of the data and do some investigation on the schema. It looks good to us, right? And now I want to point out that in Fugue, in the data flow, if we want to communicate between different steps, we must use data frame. So think about that. If we have n different files to download, how we do that? We should construct a data frame to contain these n files as n rows, and then to pass into the Fugue workflow, and to let Fugue to distribute that data frame and to download the data distributedly. So that's why we want to convert the files into a pandas data frame. Okay, the next step is very simple. Given a collection of files, how can we implement the download logic? As you can see, this is just a native Python. It has nothing to do with Fugue. It has nothing to do with any distributed computing frameworks. And we also can unit test this one. And here we just choose the first two files and let the download file to download sequentially. So how can we distribute this workflow? Actually, under the hood, we are going to make this one row as each subdata frame. So we'll have 5 subdata frames, and for each data frame, we'll apply this download to download the files. So we will partition the data and apply the transformation and then finish. So here is how we do that in Fugue SQL. But of course, you don't have to do that in Fugue SQL. Actually, even in Fugue, you can do this in a programmatical way. And as you can see that the five files are printed together. This is because using Dask, we're able to run these 5 download jobs in parallel. So, and you can see that the total download time is is under 7 seconds. This is the power of a distributed computing framework. Okay, after this, we have got this this folder, and it contains all the flights data. Now let's start to do some transformation on the data. First of all, let's load the entire folder and to print the first 10 rows to see if it is expected. And then also we want to print the row count. And then here, we just want to select a few columns, and we just want to select 50 rows and persist and yield as test data frame. Why? This is how we quickly iterate on this distributed computing problems. We always make this a smaller problem, and then to work on our core logic and apply on this small test data set. And only when it works well, we bring this logic to the entire data set. So now let's talk about this logic. So for this logic is that assume we're dealing with a pandas data frame. We just want to add 3 additional columns, and they are derived from these 2 columns, right? And here, the only thing I want to mention is that we have this line. It's called schema hint. It's a comment line, so this entire function is still native function. It has nothing to do with Fugue, but Fugue is able to recognize the type annotations of this function, and it's also able to recognize the command line of this function. And combine them together, Fugue knows, okay, what the input type is required, and also what is the output schema for this transformer. So this becomes a valid transformer for Fugue to use directly, while it is still totally independent from Fugue. Okay, now with this transformer, let's test it on the local tested data set. And this is how we do it. As you can see, we didn't specify Dask here because we just want to use the local execution engine and transform the small data using this transformer and print and see if it is working as expected. So it is working as expected. So now we have the confidence to apply this transformer on the larger data set. Let's do that. Okay. So as you can see, we change from the test to the entire data set, but other things will stay the same. And then we just use the standard SQL clause to select the columns and also rename some of the columns. And then we just persist and yield the flights. And so up to here, we have had our flights data and our metadata all in memory, persisted in memory. But I want to point out that if you are using a distributed Dask cluster, this flight data is persisted in the cluster. It's not necessarily always on the driver. So that's the power of a distributed system. You don't have to worry too much about where the data is persisted and how big the data is. The system will do the job for you. Okay, so far I have introduced the transformer. Let's talk about outputter. Outputter in Fugue is another type of extension, and it is very, very useful for visualization. So look at this function. Again, it is just a simple Python function. It has nothing to do with Fugue, but with the type of annotation, it is already qualified to be an outputter of Fugue. We can use it directly with our other standard SQL statements. Let's see how it works. So in this example, we just consume the flights, aggregate on day of year, and get average delay. And then use this extension to plot. And we do the same thing, but we just aggregate on hour of week. As you can see, this will print 2 charts. And from the second chart, we can see some cyclic pattern over a week, right? Okay, so now let's do something that is more complicated. So for this one, we just want to join flights and airlines and airports with metadata so that we can get the origin country, origin name, and desk country and desk name. Okay. And the next step, we want to have a smaller data frame where we only care about United States domestic flights. So we only need to apply another standard SQL here, and then just persist and yield this info US data frame. Okay. After this, we want to do some additional plotting visualization. So we add another extension called plot bar, and we add another chunk of EDA code. So in this analysis code, I want to mention that the interesting thing starts from here. What we want to do is we only care about the top 20 biggest carrier. We want to see how much delay they have. We want to have a rank on them. So the first step is just to aggregate on carrier and to get the count from info US, and then order by the count descendantly, and we limit to 20 because we will only care about top 20. And then we just join our info US with this top. So this is actually, we should here we should use left semi-join. But since Blazing SQL does not support left semi-join, we have to use inner join instead. But it just works fine. Okay, after this filtering, we just do the same. We just aggregate on carrier name and get the average delay, and then select the worst 10 carriers and plot. So here is the result. Okay, so we have done some analysis. Now, what about we put everything together? So here is how we put everything together. As you can see, that it's almost just a simple copy paste of the previous cells. The only difference is that we remove those yield data frames because they are no longer necessary. Everything is in the single cell, so we no longer need to yield anything. Okay, while this is running, let's talk about productionizing the whole entire data pipeline. So productionizing the data pipeline, I think one very important thing is try to modularize your logic. So here, we modularize our logic in this way. The first step is to get metadata. The second step is to load flights data and to do some basic transformation. And the third step is the EDA part, which is giving these data frames, we just do the plotting, right? So we will have 3 modules. Now let's see how we can combine these 3 modules together using Python. So here is how we do that. We just import the fsql function from FuseSQL, and for metadata, we run this metadata query without any parameter. That means we just want to use the local execution engine to get the metadata. And for flights, because it will require the transformers, right? It requires the transformers as well as the SQL. So we will run this using Dask. And we always get data frames from the first query and the second query. And for the EDA part, we will use this metadata and flights as input because this will contain 2 data frames, and this will contain 1 data frame. And they will be used by the EDA query. And we also specify n here. What does this mean? So notice here we have changed the string to a template string. We have an n here as a Jinja template. So here, if you set n equal to 30, so this will be replaced with 30. This is how we parameterize our Fugue SQL workflow. Okay, so now let's take a look at the Blazing SQL. How can we do the similar thing for Blazing SQL? So in order to run Blazing SQL, we just need to import Fig Blazing. Okay, and for the first step, again, they are just a very small CSV files. There is no need to use any fancy execution engine to run them. So we just keep them using native execution engines. And for downloading, we are going to skip them because they are already downloaded using Dask, right? So we already have this folder of files. So now how can we use Blazing to do the similar thing or to do the exactly same thing? So the only thing you need to change is here. You just change the execution engine of this FSQL from Dask to Blazing, and then you will get the result. As you can see, it's very, very fast, and the result is exactly the same. And for transformers, it is the same. You can define the transformer, you can verify it, and then you can run it. When you run it, let's firstly run with Blazing. So let me explain this. So if you are using Blazing, this transformation will be executed using local execution engine because GPU cannot directly use this simple Python functions to run in parallel. So this transformation has to happen on CPU. So it has to use the local execution engine. But there is an alternative way, which is you can specify a combination of Dask plus Blazing SQL. What does this mean? This means for SQL part, we will use Blazing SQL to run. But for the rest of the part, for example, for the transformation, we will use Dask. So in this way, you can utilize both the CPU cluster and your local machine's GPU. Okay, so next step, let's take a look at this part. What if we just change this to Blazing? And as you can see, it's a little bit faster than Dask, right? But the result is the same. And for this one, this is a very complicated one. It requires a lot of join and filtering. Dask took 40 seconds. Let's see how long Blazing takes. Only 2 seconds. That's the power of GPU. See how fast it is. And for this additional block, if we change it to Blazing, it was 11 seconds. Now it takes only 2 seconds. And the result is still the same. And for everything together, we can also change it to Blazing. So as you can see, for Fugue SQL, it's platform agnostic and scale agnostic. The only thing you need to do is to write things in the Fugue SQL way, and then you can just change that execution engine by a single parameter change. And then you are able to migrate on top of different systems, right? Okay, so while this is running, let's take a look at the final step, right? We talk about the productionization step. This is it. And for this problem, I think I will just change this to Blazing. I will keep this using Dask. I will keep this using the native execution engine. This is, I'm using Dask in this one because this has a transformer, which is expensive and which cannot utilize GPU. So I would rather utilize all the CPUs I have. So for flights, I just run with Dask. And for metadata, that's so cheap, I will just run using the native execution engine. For the EDA part, Blazing SQL is blazing fast. That's why I choose Blazing. As you can see, using Fugue SQL, we're able to change these execution engines so freely. And so you get a framework, you get a pipeline that can run in a hybrid execution environment and to fully utilize all your compute resource in the most efficient way. Thank you. That is all I want to talk about. Thank you, everyone. I think we have finished all our presentation now, and I think we can, if anyone has any questions, we're happy to answer here.
Thanks, Han. This is yeah, that kind of shows me how easy this is to, if you try to stay mostly in the SQL world, you can pretty much abstract everything out and you know, switch at will, pretty much, you know, between the engines. Whatever is, you know, fitting your work better, you have the ability and the flexibility to actually do that. So yeah, I've really enjoyed you know, working with Fugue and also seeing how it works.
Thank you.
There is a question. So Han, have you considered bringing in the decision about .run engine into the Fugue engine itself? Say you have compute heavy task like use SQL versus memory heavy ops that use Dask cluster, and let the engine choose that. So kind of like, I believe the question is, can you push that logic instead of you know, user specifying that for the engine to be more aware of what it should be using?
Yeah, that's a very good question. Actually, I also got the similar questions from my work. So how to make the execution more smart so that I can choose things differently. But for now, I think we're not that smart yet. You still have to specify for different steps. But actually in Fugue SQL, there could be an even easier way for you to specify which engine you want to run for a certain block of SQLs. I think that could help. But in general, the answer to question is no, we are not there yet. We cannot determine which execution engine to use during the execution.
Awesome, thanks, Han. Any other questions? Feel free to ask them either in the chat window here or on in the workshop Dask SQL Query channel on the Slack. I'm gonna wait there for a little while and see if we have any questions. But if you guys, we're gonna be hanging out, so feel free to ping us whenever you have a question. You can also ask questions on GitHub or find us on the Slack channels. But right now it's 8:30, so I believe we are due after 3 demos, due for a short break. So let's reconvene around 35 minutes past the hour, whichever the hour it is for you. And yeah, and then we're gonna have Snowflake and Coil present how to integrate Dask with the Snowflake engine. So see you in 5. Thanks, guys.
hey, Tom, if you don't mind, I'm going to use this time as an opportunity just to try screen sharing on a new computer. And
by all means,
things are
by all
weird.
means.
Yeah,
Sure.
great. Let's make sure this works. It seems to be okay. Fantastic.
Cool.
That's it. Thanks.
Oh, okay. Awesome.
And I'll go ahead and start sharing our presentation deck.
That works. Thanks, Miles.
Tom, I'm curious, do all of you just like have GPU laptops you work on? Like what's your like usual dev environment?
I wish. No, I'm running on Mac. So that's running AMD, which I cannot currently use for any data processing.
Okay.
But I have a standalone rig. So I have a Titan RTX over there, kindly donated by NVIDIA to me a while back. So that's my main platform that I use for any rapids, any other stuff. And then if I need to go beyond that, we then switch to the cloud offerings.
Yeah, makes sense.
Yeah.
I'm just curious. I mean, GPUs are amazing, but the accessibility makes it hard to have like full penetration. I mean, it's great. I mean, SQL is a great leveler there, right? Because you can have Dask SQL, Blazing, some other database, and it's nice you can mix and match.
Yeah.
Han's presentation was great at showing that.
I agree.
I wish an NVIDIA GPU could be inside of a MacBook Pro. That would just solve everybody's problems.
You and me both. You and me both.
Yeah.
I to this day I regret. So it wouldn't work by now, but I had the last MacBook Pro. I believe I purchased in 2013. That came with the GTX. I think at that point it was like 770 or something like that.
Yeah.
And it was a brilliant machine, but
yeah,
what can we do? I cannot solve Apple's and NVIDIA's wars, sadly. But yes, I'm 100% with you on that one.
Should we get started?
Yes, I think we are 1 minute past. So yes, let's please get started. Miles and Matthew, please go ahead and then show us the snowflake for Dask. I'm really curious about that one.
So I think maybe like before we get started, I just want to add a bit of like historical context to this whole workshop for a second. So like historically, like I never wanted Dask to be a SQL database. That was like original, like that was an anti-goal of the project. There are so many good projects and it's really, really hard. What I love about the recent talks that we've seen is that they're using Dask as a component to build or augment other efforts. It turns out you can take Calcite and Dask and Rapids and Pandas and all sorts of interstitial code, and you construct really interesting projects with it. A different option, so another sort of part of Dask, not sort of Dask as a component, but Dask as a bridge, is to use an existing database framework. So people have been doing this in Python for decades, right? We've been, ripping CSV exports out of Oracle databases or Postgres for as long as I've been coding in Python. And this talk is a bit more in that vein. How do we sort of have Dask play nicely with other databases that are already around? This has become a little bit more challenging in a couple of ways recently, because we've added scale and like doing bulk reads out of databases at scale becomes a lot more challenging. There's like interesting handoff that has to happen. It's also become a lot easier because a lot of database companies are now really excited about Python and machine learning, all the capabilities you can do with combining both of them. So this talk is going to be an overview of Snowflake, which is like a large and forward-thinking database that's really thinking about building that bridge. Then we're going to get some challenges of moving data back and forth, so it'll be more technical. And we'll give an early preview of how that's a lot easier today than it was even just a week ago. So with that, I'm going to have Miles take it off for the first half. I'll come back in the second half. So Miles, you want to introduce yourself and take over?
Yeah, sounds good. So hello, everybody. My name is Miles Adkins, and I'm a partner sales engineer here at Snowflake. Obviously, today I'll be presenting alongside Matthew Rockland here, CEO of Coiled. And so, yeah, in this session, we'll just walk through some of the challenges people run into as the size of their data grows and that want to continue to give value from their data science initiatives. And so we're going to show you kind of how Snowflake and Dask together can help you solve these problems and how to get started with implementing a solution. So as we know, data volumes today are growing at a steady clip year over year as the importance of data collection continues. A diverse ecosystem of packages have emerged, allowing all sorts of easy ways to manipulate data, most widely known being pandas, and build models that derive valuable predictions such as scikit-learn and TensorFlow. But what happens when you want to move past a single machine? How do you continue to push the boundaries of analytics and modeling techniques? The answer, we think, is Snowflake and Dask. Michael McCartney from Capital One, which is a big Snowflake customer, can be quoted saying the following. Capital One made a sizable investment to bring their data to Snowflake, but ran into obstacles when it came to deploying and developing models, something that is not native to Snowflake currently. Through a seamless integration with Dask, Capital One was able to leverage Dask's suite of scale-out machine learning libraries to handle vast amounts of data that they wish to train on. And so for those of you who are not familiar with Snowflake and the offering that we provide, I'm happy to provide a walkthrough here. So Snowflake is a scalable SQL data platform as a service, which is the culmination of 3 distinct layers working together, all deployed on your cloud provider of choice. The first layer is a storage layer. Snowflake leverages infinitely available, cheap cloud storage, such as AWS S3 or Microsoft Blob Storage, to store and replicate all of your data in a compressed columnar format. The second layer, compute, which is completely separated and independent from the storage layer, gives you instantly available processing power to tackle the entirety of your workloads, allowing you to scale up or scale out as needed. In addition, each compute warehouse is completely separate from each other as well, so even compute is decoupled from compute, allowing you to scale across workloads as needed without resource contention. Lastly, the cloud services layer orchestrates the first 2 layers to work together and manages all the meta processes to do so. You can think of this as the brain of Snowflake and enables Snowflake to be offered as a service. And so with that, with infinitely and instantly available storage and compute, Snowflake allows you to run all of your workloads on a single platform. Whether you have structured or semi-structured data, and soon unstructured data, Snowflake enables value across 6 different distinct workloads. If we focus in on the data science workload, here is a typical version of the ML workflow that we see at our customers. Snowflake comes equipped with a multitude of features to take you seamlessly from data ingest to exploratory data analysis to feature engineering and so on. When it comes to model training and deployment, this is where Snowflake relies heavily on our partners, such as Coiled and Saturn Cloud, that offer scalable Dask implementations of the main libraries that you know and love. And so with that, I turn it back over to you, Matt, to give us an intro into Dask.
Sure. I'm going to share my screen. I need you to quit if you can. Yeah, great. Let's grab this. Yeah, so I'm not going to tell you all what Dask is. I think everyone here knows what Dask is. But just to summarize what Miles was saying a little bit, right? So Snowflake is a central data storage service with a highly optimized SQL engine, right? There's, probably developer centuries inside of Snowflake's query planner. But it could benefit from some advanced operations in Python, like machine learning or sort of early data prep. And so let's think a little bit about why we might want to do this, right? So on one side, on the ingestion side, you might have data that isn't tabular. You might want to sort of throw that data with some processing into Snowflake, or you might want to run some large machine learning model on that data, say run XGBoost at scale. And Dask ends up being like a good sort of glue system to do Python at scale in lots of different diverse situations. Dask is not so great at SQL operations. We can do some, especially with some of the great work that folks have done here, but there's still these are nascent efforts. There's also no integrated storage. Dask is not itself a database. It can do awesome, GPU accelerated queries, something like Blazing, but it's not gonna sort of mix that storage and that compute layer at the same time. But Dask is very good at advanced analytics and very good at sort of non-traditional data. And so it's like a nice complementary tool. So when I say wider range of data, this is what I mean. So there's SQL-friendly data on the left, and there's not so SQL-friendly data on the right. And in lots of the talks that we'll see in this conference, a lot of them are about this sort of exciting different kinds of data. And how do we sort of pre-process that so that we can then ingest it properly into a SQL database? And once it's there, how do we then run some advanced machine learning technology on it? Whether it's RAPIDS or XGBoost or PyTorch or scikit-learn, anything like that. How do we rip data out of Snowflake, run some other distributed system on top of that data in order to train some advanced model? So those are the two sort of cases where we see Dask and Snowflake playing well together, sort of on either side of storage. And so what's really nice here is that Snowflake and Dask both focus on doing sort of one thing well, and that by combining them, we get to do actually a lot of things really well. And that goes to this sort of theme of building focused technologies and building bridges between those technologies, which I think is really where a lot of software development and ecosystem development are going. So there's a technical challenge now of how do we actually make these two things work together? How do we actually build that bridge? So there are many ways to rip data out of Snowflake and throw it into Dask. At the end, we're going to talk about a new way, which is going to be better than all the previous ways. But it's actually pretty instructive to go through the ways that exist today. That'll help us understand the problem we need to solve and the kinds of things we need to watch out for in solving this problem reliably. So first, don't use Dask or parallelism at all. Lots of data sets are small. The first rule to Dask is don't use it if you don't need to. And so there exists Python, there's nice Python Snowflake connectors you can pip install and use, and everything works just fine. This is super simple, it's already available, but it doesn't scale. If you have larger data sets, the sort of simplest thing to use is the Dask data frame read SQL capability. So this was built a few years ago by folks at Anaconda, mostly led by Martin Durant. And what this does is this breaks up a large query into lots of small queries and then runs those queries in parallel. So if you have, for example, a long time series, you might get sort of the min and max of that time series. You might cut that up into 100 different pieces, and then you'll submit little queries to Dask to read each of those different regions, 1 month of data each, for example. You can then put each of those into a Dask data frame, and that's a good way to sort of export your data cleanly from a SQL database. This uses SQL Alchemy, which Snowflake also talks to. And so it works with any database, Snowflake or others. There are some challenges to this though. So it's slow, it's backed by ODBC, which in Python usually isn't that fast. It also doesn't support complex queries. So if you have many tables that you want to join and do group bys in a complicated way, it's actually really, really hard to think of the little subqueries you should write. And so really this is only useful to sort of rip one table out at a time with Dask. You can't sort of do this you can't use the full database and use all the amazing query planning technology. You kind of have to have sort of a one table query that you want to play with. There's auth connection information in the string, like figuring out how to merge auth systems between different distributed systems is hard. And then finally, there's also a risk of inconsistent results. So because you're doing lots of little small queries rather than one big query, like someone could be writing at the same time and you could get nonsense answers or answers that are incorrect in subtle but dangerous ways. So this is a super useful general purpose way to read from any scalable database, but it's got lots of problems. It's not what we'd recommend. More recently, the good folks at Saturn published their documentation on how to sort of do this process manually using Dask delayed. This is more or less the same process, but rather than using the Dask data frame function, they're sort of doing it piece by piece. This has sort of lots of the same pros and cons, but it's maybe good if you want to sort of think about, educationally, what are we actually doing under the hood? The other sort of paradigm of doing this is to do bulk exports. And so this is really common in the wild. Again, we've seen this for decades, even with sort of older systems like Oracle or Postgres. People will run some query and then they'll just dump that file, that query results to some easy to read file. So I think the pandas read CSV function is as good as it is just because everyone was ripping data out of SAS and out of Oracle into pandas. This is usually, so this is great in a few ways. You can do complicated queries. You can have a complicated join and you can dump that to a CSV file. It's usually really, really fast because everyone has really focused on how to write to common file formats like CSV or Parquet. And it's a consistent output, right? Because the database is running one query and not 50 queries. As we've shifted to the cloud, as we've shifted to distributed data sets, we tend to see Parquet take over more from CSV, which is fantastic. And it's great because everybody reads and writes Parquet today. Spark, Dask, Snowflake, everybody. The challenge of this, though, is that now you have this extra data set that you need to manage. And that management ends up causing lots of pain. It causes pain because you got lots of copies, and that might be costly. It also causes pain because that data set gets out of date. Maybe that data gets updated. Maybe you share that data with someone else. It might be 4 or 5 different copies of that data around. In practice, your database admins get very, very sad when you do this because there's a lot of advantages to a database you're losing out when you start managing copies of your data. And so we want something that gives us the same power as a direct bulk export, but that doesn't have us manage it, that has the database itself manage it. And that brings us to option 4. So that's the new thing that we're sort of announcing today, although it's still in preview mode. So option 4, there is a Dask Snowflake package, which is sort of in private beta currently. And it uses a direct bulk distributed read API that Snowflake engineers produced, and then it reads that into Dask data frames. This provides fast parallel reads. It auto partitions and supports complex queries, and it is automatic cleanup and lifecycle management. So it's kind of the best of both worlds. I'm going to show a quick video of this. Now it's also a good time to mention that I didn't do any of this work. I'm actually filling in for 2 engineers, James Bourbeau, who's currently giving another tutorial right now in the conference, and Florian Yatta, who is currently, I think, driving his girlfriend to get a COVID vaccine. So you all get me instead. But this is a great video from Florian. It's about 2 minutes, and it shows us how these 2 technologies work together. So everyone works at Coiled. Florian's setting up a Dask cluster on the cloud in the same region where his Snowflake workspace lives. So he's getting a lot of local compute happening and really benefiting from that sort of services approach in both companies. He's then authenticating to Snowflake in however he would normally authenticate. Here he's using environment variables, which we do not recommend, but it's just sort of the easiest thing for an example. Then he's got a SQL query. And notice this is a complicated SQL query, right? Then he's loading up the Dask Snowflake package, which consumes a query string and produces a Dask data frame. Then we're going to execute this query. So that query now shows up on the right. We're looking at the Snowflake dashboard. You see that it's running currently. Let's take about 40 seconds. See that query has arrived inside the Snowflake dashboard. And that's the same query that we were playing with before. And recall again that this is a complicated query. This isn't just ripping out one table. It's a full system. And what's nice here is that we get to use all of Snowflake's advanced query planning capabilities and what they're really, really good at. We get to work on with a really efficient, really mature database query planner. And the result comes back now not as some giant internal result set, but now as a Dask data frame that we can do whatever we want to with. There's about 10 million rows in this data set. It's been partitioned in about 400 partitions. And now we can start looking at that and playing with it. So again, this looks and feels a lot like a Dask object. And only now are we starting to use Dask, because now we've switched on the right from a Snowflake dashboard to the Dask dashboard, and we can do lots of fun things with Dask. So for example, we might want to train an XGBoost model with this data set that we've just pulled from Snowflake. And Dask, of course, is very, very good at now pulling data from Snowflake, setting up XGBoost, doing a bit of feature engineering, a bit of training and testing split, and then training an XGBoost model at scale and giving us back a result. So what's really, really slick here is we're able to use both systems in the way they were designed to be used at full scale in about a couple of minutes. Florian is doing all this from his laptop, and everything like auth and security and performance were all handled for him automatically. So that's the demo. Let me talk a little bit about what happened there under the hood. So we have a Python client on the left, and that sent a SQL query up to Snowflake. Snowflake then did the magic that it does, and it produced a distributed result, and it's storing that in some sort of side area. It then sends metadata for all those result chunks back to the Python client. Python client sends that to the Dask workers, which then go on and query that data directly from Snowflake. So this is very much like that bulk export approach that we saw with Parquet and S3. The difference here now is that Snowflake owns these results. And so we actually don't have direct access to them. We can pull data from them for computation, but Snowflake owns the access, it owns the lifecycle management. And as a result, Snowflake will also clean it up automatically. And this saves us from ourselves, which is the challenge we ran into with the Parquet bulk export option. So that's it. I'm going to hand off to Miles for the summary, and we have a few minutes for questions.
Yeah, so with that, we kind of give you a quick, gentle introduction to the Snowflake architecture and how we are a fast and easy to use SQL data warehousing service. We obviously have engineers who are thinking about the Dask community and are looking to develop and further improve that Snowflake Python distributed fetch connector. And if you're interested in getting your hands on the private preview, feel free to fill out the form. I've posted it in both the Slack channel here and the Zoom chat. We're targeting a Q2 private preview for the Snowflake Python distributed fetch connector. And then the second half of 2021 is when we expect to go general availability. And so with that, happy to open it up to any questions that you might have.
I think we are almost on time. I see that there was a question, but I think you already answered that, Miles, from Robin about when to expect the native Dask Snowflake support. I keep scanning from both sides, the chat and the Slack channel. I don't see any other questions for now. But if any other question shows up, I wanted to say thanks everyone for attending. Thanks Matt, Miles, Han, and Nils for hosting this. This is great. It was a really great pleasure to to be part of this and then showcase our technology and learn more about the other technology. So that was a really great thing. I see one question that showed up. So did you guys mention anything about BigQuery integration with Dask? I think that question goes to Miles and Matt.
There are GitHub issues about BigQuery integration with Dask. You can use the existing SQL Alchemy connection if you want to. Google folks have reached out in the past. If you have a Google support person, you should mention that. Clouds and other large vendors really respond to customer requests. So if anyone is a customer of a vendor and you want Dask support, the best thing you can do is to start bugging them And that ends up like, that does get recorded, and like they say, oh, we have 12 customers who want Dask support. Now we care about it. There's a GitHub issue on that same topic if you go to the Dask issue repository.
Gotcha. Awesome. Any other questions? Let's see if something shows up. Okay, so there's another one I see in Slack. Do you have any insights on migrating from existing traditional big data infrastructures to Dask SQL ecosystem?
I think we've seen a few, there's not an ecosystem here, right? There's lots of different options, right? We've seen things like Dask SQL and Blazing, which are designed to work with existing data stores, right? So you can, maybe you can, if that pre-existing technology provides bulk exports, you can use those on top of that, the older technology. If you want to upgrade to a new technology, something like Snowflake, and you want to move your data, I'm certain that Snowflake has countless documentation on how to move from any system available into it. But it's interesting, it's important to note that difference though, between data storage and data computation. And when we say SQL or databases, we actually kind of mean both at the same time.
Yeah, awesome, thank you. Okay, so I see that Dask Tracks 3 is saying we have no time left on the Zoom, so I guess we gotta wrap it up. Once again, thank you.
Thank you for organizing, Tom.
Oh, that's Nils and Han. So I was just playing along, which was quite fun. Thanks, guys. Appreciate it.
Then,
thank you, everybody.
Awesome. Thank you. Have a good one.
Thank you.
Enjoy the conference.
Have a good one.
Bye.
Bye.
Thank you. Bye-bye.